All right, these are the notes for Unit 1, Day 9, and this was part of the con from the previous day that you should have complete for today. These are kind of the building blocks of what we're going to talk about today, so you really need to be very proficient at these skills. So if you haven't completed these yet, I would finish those up immediately so that you are really proficient at those skills. Definitely need those as building blocks. The notes for today start on page 24 of your packet, and our topic for today is rates of change and tangent lines. So a rate of change is a rate. It's a rate of change is like a meters per second, if going back to physics. It's how much something changes in a given amount of time, most often. And a tangent line, if you recall, is a line that touches a curve at one point. So we're taking a look at rates of change and tangent lines. And the essential question is, how can we calculate slope with only 1 point? So if you remember calculating slope in algebra, you needed 2 points. Why? How can we do that with only 1 point? That's really the question. Okay, so let's take a look at some definitions. First rate of change we're going to talk about is something called the average rate of change. And the average rate of change of a function, so I'm trying to color code here, of a function over an interval is the amount of change divided by the length of the interval. So remember, intervals are domains, and those are x coordinates. So the length of the interval is the difference in the x coordinates. The amount of change of the function are the y values. So the amount of change is the difference in the y values. So the difference in the y values divided by the difference in the x values. That should sound familiar. Okay, so we also call that the slope of the secant line. I'll get back to the word secant in just a minute. So the average rate of change of a function, here's the definition. The friendlier verbiage, or really I would say the friendlier equation, is y2 minus y1 over x2 minus x1. So notice the color coding I'm doing here, right? The amount of changes are the y values of the function, and the length of the interval is the x value, or the domain of the function. So ROC is for rate of change, AVG is for average. So this is the average rate of change. That's how we kind of note it when we're doing that calculations. Okay, sometimes we call it rise over run, right? That goes back to algebra for sure. Okay, so other synonyms. I call this the algebra slope, right? That's exactly where it comes from. It's also called, and we said it up here in the definition, it's also called the slope of the secant line. A secant line is different than a tangent line. A secant line touches the curve in 2 spots. In other words, we need 2 points, right? We need x1 comma y1 and x2 comma y2 on the function. So the secant line is going to touch that function in 2 points. We also, if we're referring to this, and I kind of alluded to it a little earlier when I talked about physics, if we're going to put some context in it, the most common context is to put motion as part of the problem. And so this is also called the average velocity, because it's the rate of change of position. Is most commonly referred to as with context. Okay, so let's do a calculation. So we have example 1 here. Is we're applying the definition of average rate of change. This is not in your pod, obviously you're taking notes. So we have function f of t is t squared minus 3t. So here's f of t, right? So just a quick check here. T squared, this is a quadratic or a parabola, that makes sense. If I factored this, it would be t times the quantity t minus 3. So it would have zeros at 0 and 3, right? Those are the solutions. So that checks. It opens upward because t squared is positive. So we're just doing kind of a visual check. Does this function match this picture? And the answer is yes. Okay, so f of t is equal to t squared minus 3t represents the position of an insect as it crawls on a picnic table. Calculate the average velocity of the insect over the domain from 1 to 4. draw the secant line representing this value. Label its slope as average velocity. So when we talk about, let's talk about the insect. First of all, this is with respect to time. So these negative values don't even apply, right? So we can see that this insect starts at the origin because its position is 0 at time 0. It crawls in the negative direction. And then it looks like maybe a little more than 2 meters away. And then it stops and turns around and comes back to the starting point, and it takes 3 seconds to do that. And then it passes through the starting point and keeps walking away from us. Okay, so that's what the insect is doing. Okay, so average velocity means algebra slope. So when you see this verbiage, average velocity, you're thinking, I have to do a rise over run calculation. I have to do a y2 minus y1 over x2 minus x1. Here's my domain, 1 to 4. These are the x coordinates. So let's go ahead and then we just know that we're going to draw and we're going to label, right? Let's go ahead and draw the points. Here's the point at x equals 1. Here's the point at x equals 4. Let's connect the line. That's a secant line. Touches the curve in 2 points. We call that a secant line. We're going to label it average velocity. So we've done all of this stuff in blue. Again, I'm color coding, right? All the stuff we've completed in blue. All right, let's do the average rate of change. So the average rate of change is going to be f of 4 minus f of 1, right? That's y2 minus y1 over 4 minus 1, x2 minus x1. So how much is f of 4? F of 4 is 4, right? If I put 4 here, it'd be 16 minus 12. So it's 4, and f of 1 is negative 2, right? If I put 1 here, I get 1 minus 3, it's negative 2. So minus a negative 2, that's the tricky stuff, right? Because average rate of change has a minus on the top and a minus on the bottom. Those are subtraction signs. This is a negative position sign. Okay, so we have then 4 minus negative 2 is 6. 4 minus 1 is 3. 6 divided by 3 is 2. So this slope is 2, right? And we can see that. We can go up 2 over 1, up 2 over 1, up 2 over 1. So we know that that slope is 2. So that's the average rate of change. I don't see any units indicated, so we don't need to put units on the answer because there's no units indicated. If there were units, we'd need units on the answer. So that's average velocity. It's what we did in algebra all the time. Okay, so this is the question though. This took 2 points to find a slope. Our central question is that we want to calculate slope with 1 point right here. And that's where the tangent line comes into play, because we know the tangent line only touches the curve in one spot. So if we could draw a tangent line accurately right here and find its slope, then we would have the slope at location x equals 1. And that's what we're going for. And so, so this is, if you notice, I'm gonna go back screen, look at the parabola, look at the graph, and I'm gonna go forward a screen. Look at the same thing here. This is the same function. This is my secant line. I'm gonna go back again. I probably should have maybe made that blue, but I didn't. But that's my secant line. So what I'm gonna do is this is actually a little movie. Okay, that's the average rate of change. And I'm instead of 1 and 4, like we had in the average rate of change problem, I'm labeling them using generic values, right? I'm calling this location A. A is 1, okay? And so this is f of A. F of A is negative 2. And this is going to start out by being 4 and 4, right? X is 4, Y is 4. But really, it's location A, and then we've moved to the right a certain distance h. And this distance h is variable. I'm going to actually bring this point back to this point. So let's let this kind of play out here. So if we looked at our average rate of change, and if I just call this a plus h, we know this is 1 plus 3, right? We're out here at 4. But if I just called it a plus h, and I wanted to calculate the average rate of change, then I would take the y value, f of a plus h, minus the minus the y1 value, f of a, all over the x value, a plus h, minus the x value a. And of course, if we can't really simplify this right now, we're going to though, because we know what the function is. But this just by inspection, a plus h minus a is just h. Okay, so the way we get the slope at a point is we take that expression. So I've simplified the denominator. We take this expression for our secant line, and we take, there's that distance h. Just, you know, plus h just means I've moved to the right h units. And we are going to take the limit as h goes to 0. So in other words, we're going to close this gap between the 2 points. Okay, that's what this is saying. As h approaches 0, as the point starts here and we start to slide back along the function, this h is going to close up and go to 0. So we're going to use what we know about limits to find the slope just right here at 1. So here is the animation. So there's my location A. And then I'm going to come up here and grab this point, and I'm going to slide it back. So right now, the secant line, we did this calculation already, but this is dynamic, so I'm actually going to be able to slide that red point all the way back to 1. So as we're sliding that red point all the way back to 1, the h is closing up and going to 0. Okay, and notice the slope is changing dramatically, right? If I stop there, I can get a slope of 0 because I'm going straight across the graph. And I bring that all the way back to A. And when I do, because of the calculation that I have up here for the secant line, the calculation bottoms out, right? Because the bottom is A minus A, which is 0. But if I take the limit, I get the slope here. We can obviously see that this is down 1, right 1, down 1, right 1. So we know that the slope at location A of the tangent line, we've changed the terminology of that line because it's now only touching the curve in 1 point. So it's now a tangent line, and the slope of that line is -1. Down 1, right 1, down 1, right 1. So we're going to actually go through this limit process with the function and show this algebraically that it turns out to be -1. And so we're going to do that on the next screen. So let's talk about the definition of the slope of a curve at a point. Going back to here, this is the definition right here. It's just that limit notation. So a slope of the curve at a point, or in other words, there are some synonyms, we'll get to those in a second, is literally that definition. Okay, so get that down. And again, it's this f of a plus h minus f of a over h, which remember this used to be a plus h minus a, right? But we simplified it. This is just slope, and we're taking the limit of this expression, which means we have to have a function to plug up here, up top. We have to have a function that we can simplify and do some of our limit processes that we had on our flowchart, so that we can eventually evaluate it at when h is approaching 0. Okay, our other synonyms then, we call this the slope of the tangent line, because we know as we close that gap, that secant line becomes a tangent line because we're at 1 point. We also call this the instantaneous rate of change. Okay, because it's at 1 point, in our example, it's x equals 1, right? Because it's at 1 point, we call it instantaneous. We had the ROC designation, so we just call this ROC. If we want to give it some context, we could call it the instantaneous velocity, or just velocity. So when we drop the word instantaneous and just call it rate of change or velocity, it's implied. So we're going to use, like I said a little earlier, we're going to use what we know about limits to calculate this. Okay, so the last synonym then, we've got 1, 2, 3, 4 synonyms. It's a lot. The last synonym I use is something called the limit method, because that's the method we're using to evaluate and get that value for the slope. Okay, so same function, t squared minus 3t. Okay, and we want to say, it says insect crawling on a picnic table. We got that. Find the insect's instantaneous velocity at t equals 1 second. So right here. So that's my a value. I see the term instantaneous velocity. I know it means the limit method. So when you correlate that verbiage with this, then you've correlated this term with a method, a process that we can use to get the answer. T equals 1 is your a value. So this is where those cons are coming into play that I mentioned with the building blocks, because one of those cons was evaluating expressions. And so we have to evaluate these expressions relative to the function. So that's the first thing we have to do. So we have, these two are the two things in the numerator. So we know a is equal to 1. So f of a plus h means I want to find f of 1 plus h. So I'm going to put 1 plus h here and 1 plus h here for t. So 1 plus h squared minus 3 times 1 plus h. Right, that's the function. So I've got to FOIL this out. Remember, we got to FOIL these things, right? These are binomials. That's 1 plus h times 1 plus h. Okay, it's not just 1 squared plus h squared, right? We need cross product terms there. So this is, take a second and do this simplification on your own and check your answer with my answer. Okay, if you're tuning in, I'm assuming you've tried the simplification on your own. Okay, so we know that this is the overall simplification. We know that this is 1 plus 2h plus h squared, and this is minus 3 minus 3h. So that's where we get the minus 2 minus h plus h squared. So that's the first piece of the puzzle. Second piece of the puzzle is I need f of a, okay, which means I need f of 1. So take a second and calculate that. Okay, if you're coming back now, I'm assuming you've calculated f of 1. We can actually do this two ways. We can put 1 here and get a value of 1 squared minus 3 times 1, which is negative 2. Or we can look in the graph and see that f of a is negative 2. Either way is fine with me. A lot of times we won't have the graph though. Okay, so these two things go in the numerator. Notice this has a minus 2 and this has a minus 2. That will always happen. So when you calculate these two things, if you don't see the same value here and here, you've done something wrong. Go back and recheck your substitution and simplification, because this will always happen. All right, so let's use the definition. Definition is the slope is the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. So we're setting that up. There's f of 1 plus h minus f of 1 over h. Now, the reason why I said that you will always have this repeating number is because minus a negative 2 is positive. These will always cross out. Minus 2 plus 2, those will always cross out. You'll be left with h's all over the place. And that's specifically so that we can use a simplification technique from our flowchart to evaluate the limit. So let's simplify this. So now we're left with minus h plus h squared over h. So now we can use the factor and cancel method. This is factorable. I can factor out an h. So this is going to be h times the quantity negative 1 plus h over h. And that's super duper important. These steps will always be the same. You'll be able to set up, simplify, factor, and cancel. This is super important because we know that fractions are problematic when evaluating limits. So if we can factor, then we can cancel and we can get rid of the fraction. That is super important. That makes things super easy. Now all we have to do is evaluate the limit as h approaches 0 of negative 1 plus h. I can plug 0 in here and get a finite answer now. So I know that my slope is negative 1. So I can go back to my point of tangency, set up in this case, since we have context, right? We've been asked to find the instantaneous velocity. We can call this instantaneous velocity. I can set up my slope of negative 1, right? Down 1, right 1. Let me reverse that. Let's do that again. Down 1, right 1. And now I can draw my tangent line accurately. So this slope of this line represents the instantaneous velocity of the bug. It's traveling to the left at this point, right? We said it was traveling away from us. It's traveling to the left at 1 meter per second. I'm just making up units now. But when the time is equal to 1 second. So this limit method is really going to be our meat and potatoes here. because we need to start talking about instantaneous values. Okay, so the other thing is, let me go back a screen. The other thing is writing the equation for this tangent line. What's its slope? What's its intercept? Or more conveniently, we now know its slope and we have a point. And that's going to be the most convenient thing to use. So we have a slope and we have a point. Visually from the graph, we have an intercept. So we could use slope intercept form here, but I really want you to get in the habit of using slope point, because this is going to be far easier for you in calculus than slope intercept. Finding B is always difficult unless you have a drawing, unless you have a graph. And we very rarely have graphs. I'm just trying to transition you from visual to algebraic. So get used to this. This is written on an anchor chart at the front of the room, right above the bulletin board. So you always have access to it, even during tests. I don't take that stuff down. So keep in mind that you always have access to that. Okay, so all we're doing is plopping in a number for m, x1 and y1, done. We walk away and we consider ourselves done. So plug in the slope, plug in the x and the y values, you're done. You don't have to simplify this goofy looking stuff. If you want to keep it that way, that's fine. There's your answer. There's your slope. There's your equation for your tangent line. Sometimes it asks you to write an equation for a normal line. Normal means perpendicular. So that means this, right? It's going to go, instead of down to the right, it's going to go up to the right. And it's going to be a 90-degree angle with this red line here. So we need the perpendicular slope, which is the opposite reciprocal, right? So opposite means it's the opposite sign, so it's positive. Reciprocal, 1 over 1, the reciprocal is still 1 over 1. So that's going to go up 1 and right 1, and that's going to be a normal line. It really doesn't have any contextual meaning for this problem, but see how easy it is to write the equation for the normal line when you stick to the slope point form. All you're doing is changing the slope, going through the same point. So you're just changing this from a -1 to a +1 and you're done. The normal line has a different intercept. So if we tried to use y equals mx plus b, we'd have to find a different b, and that's a lot more work. That's why this form of the equation of a line is so handy. Okay, when we get back into the classroom, we'll work a few problems to get comfortable with this limit method for instantaneous values.